Hi everyone. Let's compute definite integrals using their definition. What was that definition? I believe that the definite integral of a function f of x on the interval from a to b is given by the limit, as n goes to infinity, of the sum starting at 1 and ending at n of f of xi star times delta x, where xi star is any sample point in the ith subinterval of AB, and delta x is the length of each subinterval. It is easy to compute the length of each subinterval because delta x is given by the length of the interval AB, which we compute by subtracting a from b, and then dividing it by the number of subintervals. F of xi star gives you the height of the ith approximating rectangle. Delta x gives you the width of the ith approximating rectangle. This means that when you multiply these two values, you get the area of one approximating rectangle. This sum tells you to add the areas of all of the approximating rectangles. And the limit tells you to compute the limit of a sequence of approximations that use more and more rectangles. If none of this made sense, I suggest you watch my previous video in which I explain this limit definition of the definite integral. Before I can show you how we can use this limit definition, we need to know two facts. The first fact says that if you want to add the first n positive integers, instead of adding them one by one, you can use the following formula. For example, if you want to compute the sum starting at 1 and ending at 6, which is the same thing as saying 1 plus 2 plus 3 plus 4 plus 5 plus 6, instead of adding them one by one, you can take the last number, which is 6, multiply it by the next number, which is 7, and divide these things by 2. 6 divided by 2 is 3, which gives you 3 times 7, which is 21. The second formula, the second fact, says that if you want to add the squares of the first n integers, you're supposed to use the following formula. While we are not going to prove why these two formulas are true, I can quickly show you why the first one could be true. There are 6 numbers here. I can pair them up. I can pair the first one with the last one. I can pair up 2 with 5, and I can pair up 3 with 4. Note that each pair, if I add them, gives me 7. The first pair, 7. 2 plus 5, also 7. 3 plus 4, also 7. Altogether, I have 3 pairs of 7. That is why the formula gives me 3 times 7. Let's see if we can use these together with the limit definition of the definite integral to compute definite integrals. In this problem, we must evaluate this integral using the limit definition. Let us start by visualizing this. We are given an interval from 0 to 3. We need to divide this interval into n equal subintervals. This means that each subinterval will have the length delta x, which can be computed by computing the length of the entire interval, which is 3 minus 0, and dividing it by the number of subintervals, which is n. This gives us 3 divided by n. This means that the first subinterval has the length 3 divided by n. The second subinterval has the length 3 divided by n, and so on. Because this number right here is 0, the next number which separates the first subinterval from the second one must be exactly 3 divided by n. The next point which separates the second subinterval from the third must be 3 divided by n plus 3 divided by n, which is 2 times 3 divided by n. The next one will be 3 times 3 divided by n, all the way to the last one, which will be n times 3 divided by n, which rightly gives us 3. Now, the limit definition of the definite integral says that if I want to compute the definite integral from 0 to 3 of any function f of x dx, I must compute the limit as n goes to infinity of the sum starting at 1 and ending at n of f of xi star times delta x, where xi star is any sample point in the ith subinterval. For example, x1 star will be any sample point from the first subinterval. x2 star will be any sample point from the second subinterval, and so on. Because I'm allowed to use any sample point I wish from each subinterval, I will choose the endpoint of each subinterval as my sample point. The first subinterval will have a sample point 3 over n. The second subinterval will have a sample point 2 times 3 over n. And in general, the ith subinterval will have the sample point I times 3 divided by n. Which means I'm going to rewrite this as the limit as n goes to infinity of the sum starting at 1 ending at n of f of I times 3 divided by n times delta x. I can simplify a few things here. I know my function. The function was x, which means f of x equals x, which is the same thing as saying that f of I times 3 divided by n is the same thing as just I times 3 divided by n. Instead of writing this, I can simply write I times 3 divided by n. Instead of delta x, I can write 3 divided by n. This gives me the limit as n goes to infinity of the sum starting at 1 ending at n of I times 3 divided by n times 3 divided by n. 3 is a number. N is a number. I can multiply these and I will get 9 divided by n squared. And I will factor those outside of the sum. And I will get limit as n goes to infinity of 9 divided by n squared of the sum starting at 1 ending at n of I. We know what this is. This is the sum of the first n positive integers. We had a formula for this. We know now that I can rewrite this expression as the limit as n goes to infinity of 9 divided by n squared times, and instead of this sum, I will use the formula from the table above. The formula was n plus n plus 1 over 2. N times n plus 1 over 2. And I get n times n plus 1 over 2. Let's simplify this. 9 is a number, 2 is a number. I can take those numbers outside of the limit, and I get 9 over 2 limit as n goes to infinity of, let's multiply the numerator, n squared plus n divided by n squared. To compute this limit, I look at the leading terms. The leading term in the numerator is n squared. The leading term in the denominator is n squared. Because these are the same, the limit of this entire expression as n goes to infinity is 1. Altogether, I get the answer 9 over 2. Note that this answer makes sense. This definite integral computes the area of the region under the graph of the function f of x between 0 and 3. If I was going to draw the function f of x equals x, I would get the following. I have the y-axis, I have the x-axis, and the function is y equals to x. That was our function. I'm supposed to look at the region between 0 and 3. To compute the area of this region, I can use a formula for the area of a triangle. The base is 3. The height is also 3 because the height of this function equals the value of the function at 3, which is 3. I get 3 times 3 times 1/2, which gives me 9 over 2. Let's see if we fully understand this by completing one more problem. If you would like to try this problem on your own, stop the video now. You can also download these notes using the link in the video description. This time we are given the function x squared. The interval is still from 0 to 3. This means that the length of each subinterval, delta x, will be 3 minus 0 divided by n. Just like before, the length of each subinterval is 3 divided by n. Just like before, we are also allowed to choose any sample point in each subinterval we wish. I will again use the endpoint of each subinterval, which means that xi star will be given by I times 3 divided by n. The limit definition of the definite integral says that to compute the definite integral from 0 to 3 of any function f of x dx, we compute the limit as n goes to infinity of the sum starting at 1 ending at n of f of the sample point times delta x. We already know what a sample point is, and we know how much delta x is. I can then rewrite this as the limit as n goes to infinity of the sum from 1 to n of f of I times 3 divided by n times, and instead of delta x, I can write 3 divided by n. My function is x squared, which means f of this expression must be this expression squared. This gives me the limit as n goes to infinity of the sum starting at 1 ending at n of I times 3 divided by n squared times 3 divided by n. Note, 3 divided by n squared gives me 3 squared divided by n squared. If I multiply it again by 3 and by n in the denominator, I will get 3 to the third power divided by n to the third power. Let me factor that number outside of the sum, and I will get the limit as n goes to infinity of 3 to the third power divided by n to the third power of the sum starting at 1 ending at n of simply I squared. The only term that is left is I, the one that depends on I. Everything else that doesn't depend on I can be factored outside of the sum. At the beginning of the video, I gave you a formula for this sum, the sum of the squares of the first n positive integers. This means I can rewrite this limit as the limit as n goes to infinity of 3 to the third power, n to the third power, and instead of the sum, I will use the formula. The formula was n multiplied by n plus 1, multiplied by 2n plus 1, everything divided by 6. Now I can simplify this expression. That gives me the limit as n goes to infinity. Let's write the numbers together, and I will have 3 to the third power divided by 6, and then let me write n's together. n plus 1, 2n plus 1, divided by n to the third power. Because this is just a number, I can factor it outside of the limit, and then I will focus on computing the limit of this expression involving n. 3 to the third power is 27, which means I can rewrite this as 27 divided by 6 times the limit as n goes to infinity of n times n plus 1 times 2n plus 1 divided by n to the third power. Because this is the limit at infinity, I can simply look at the leading terms, at the behavior of the leading terms. The leading term in the numerator would be n times 2n, which gives me 2n to the third power, which means this equals 27 divided by 6 times the limit as n goes to infinity of 2n to the third power divided by n to the third power. N to the third power divide out, and I simply get the limit of 2. The limit of 2 is 2, which gives me 27 divided by 6 times 2. 6 and 2 divide out, giving me 3 in the denominator. 27 divided by 3 is 9. This shows that the area of the region under the graph of the function x squared between 0 and 3 must be 9. This was a lot of work. Computing definite integrals using their limit definition is difficult. In the next few videos, I will show you how you can compute definite integrals in other ways.